Hello, today we're going to be talking about projectile motion, so let's jump right in. For introduction, the purpose of the experiment is to measure the effect of drag affecting a projectile motion of an object using a computational model. Then the fundamental physics principles we're going to be using are going to be drag, which is going to be negative b in our experiment. And the projectile motion is going to be given by velocity, which will determine the speed and direction of the object at a given time. Position, which is going to tell us where the object is at any time. And the net force, which is going to be the sum of all forces acting upon the object. And for our results, we're going to see that our computational model was not very accurate and the drag was exaggerated. For methodology, first we're gonna be recording a video, then we're gonna put it in Tracker so that the computer knows where the object is. Then we're gonna be developing a code to make the computational model, and we're gonna be comparing Tracker and the code. So Tracker was developed using Axis, which is gonna be up for the positive Y direction, right for the positive X direction, calibration stick, which is gonna tell the computer the scale of our experiment, which in this case, this blue line represents 20 centimeters or 0.2 meters, and these red points are going to be where the object is located at any given time. So the code was developed first defining our variables. The initial position of the ball is going to be the origin to make our lives easier, and the initial velocity of the ball is going to be found using average velocity, which is f final minus f initial over 2, and these values can be found in Tracker. Then to develop the actual code, first the drag force is going to be updated depending on the velocity of the object, and this is done so using the formula negative b times velocity squared times the direction of velocity. So the drag force is going to be opposite to the direction of the velocity. Then F net is going to be the force of gravity plus the force of the drag. The ball velocity is going to be updating using the velocity update formula, which is v final equals v initial plus F net times time. And the position of the ball is going to be updating with position update, which is final position equals initial position plus average velocity times time. For our results, we're going to see that our graphs differ quite a bit, mainly because of this point right here, which is the peak in our computational model. It's close to 0.2, but in Tracker we see that this peak is closer to 0.3 seconds instead of the 0.2 seconds. And why is this? Well, this is because the effect of drag was not very effective in real life as predicted with the computational model, probably because the object was in the air for too little time, for less than 1 second. So to answer some questions, is terminal velocity achieved in this experiment? And the answer is no, because the object reaches the ground before it accelerates enough. To reach terminal velocity, the object will have to been falling for a much longer time, and the object will have had to reach its maximum velocity, the maximum amount of force that gravity can do on it, in which in that case the velocity will be constant because it will be at its maximum, and then Fnet would equal 0. So what if the object was thrown straight up? Would it take longer, shorter, or the same amount of time as the original experiment to reach the ground? Well, the object thrown vertically is going to take longer to reach the ground. Because the initial force is not directly completely upwards, there's no horizontal component. So gravity is going to take a longer time to exert more force than it. And another way we can see it is with the monkey and hunter problem. If the monkey falls out of the branch when the hunter throws the projectile, then the projectile will hit the monkey. But if the monkey jumps first from the ground and then goes up and then down, then the projectile is going to go below the monkey. So in conclusion, our computational model was not accurate because the drag was exaggerated in the computational model, and we should have given the object more time in real life to do its motion. Thank you.